Welcome back. In this video, we're going to look at examples of determining the convergence of geometric series. Let's get to it. All right, so here's our first example. We want to write the geometric series and determine its convergence for the following. And so we have 2 plus 6 plus 18 plus 54 plus 162 and so on. And so since we're told that this is a geometric series, right, we want to write the geometric series and determine its convergence, we know that there's going to be some kind of common ratio between each of these terms. In other words, remember that for a geometric series, that you get the next term by multiplying the previous term by a specific value known as the common ratio. And so the quick way to find that is just to divide each term by the previous term, except for the first term, of course. And so let's look at the first two terms here. If we divide 6 by 2, that's equal to 3. Then if we look at 6 and 18, 18 divided by 6 is equal to 3. And then if we look at 18 and 54, 54 divided by 18 is equal to 3 as well. And if you were to divide 162 by 54, that would also be equal to 3. And so what we find here is that the common ratio for this geometric series is 3. And we label that with the letter R. So we'll say R is equal to 3. Okay, so now that we found the common ratio, we can rewrite these terms as a geometric series. And remember that a geometric series is in this form. We will have the sum from n equals 0 to infinity of some constant multiple a times the common ratio to the power of n. And so the first couple terms of the series would look like this. And so can we see how each of these terms would match the form of the terms of a geometric series? Well, first off, since we're starting with n equals 0, we know that the first term will be a sub 0, and then the next term will be a sub 1, and then we have a sub 2, and then a sub 3, and so on. And so for these terms here, we know that 2 will be a sub 0, 6 will be a sub 1, 18 is a sub 2, 54 is a sub 3, and 162 is a sub 4. And so if we look at those a little more closely, we have a sub 0 is equal to 2, a sub 1 is equal to 6, a sub 2 is equal to 18, a sub 3 is equal to 54, and a sub 4 is equal to 162. Can we rewrite each of these terms to be in the form of these terms for a geometric series? Well, remember, this first term here, where we just have a, that would technically be multiplied by r, the common ratio, to the power of 0, because with each term, the power of r increases by 1. And so if we follow that pattern for these terms, we could rewrite 2 to be 2 times the common ratio of 3 that we found to the power of 0, because 3 to the power of 0 is equal to 1, and 1 times 2 would be 2. Now for 6, we know that 6 is equal to 2 times 3, and 3 is to the first power, and so that matches the form of the second term. And then for a sub 2, 18 is equal to 2 times 9, and 9 is equal to 3 squared. So if I rewrite that, we have 3 squared. And so that matches up with this term of a geometric series. And so it's safe to say at this point that the rest of our terms are going to follow that pattern as well. Each term of the series increases by a factor of 3. 18 times 3 is 54, so this will be equal to 2 times 3 cubed if we multiply by another 3, right? 3 squared times 3 will be 3 cubed, which means that 162 is equal to 2 times 3 to the 4th power if we multiply 54 by 3 to get 162. And so we can see for a fact that our terms are in the form of a geometric series where a is equal to 2 and r, the common ratio, is 3. And so we can say that these terms would be equal to the sum from n equals 0 to infinity of 2 times 3 to the power of n. Okay, so this is a solution to the first part of this example. We wanted to write the geometric series to represent these terms, but now we want to determine the convergence of this geometric series. And so remember, the convergence of a geometric series is based on the common ratio. If we have a geometric series, a times r, the common ratio to the power of n, it will converge to a divided by 1 minus r if the absolute value of r is greater than 0 and less than 1. The less than 1 part is the important part to remember. But the geometric series will diverge if the absolute value of r is greater than or equal to 1. And so if we go back to our example, in this case r is equal to 3, and so the absolute value of r is equal to the absolute value of 3, which is equal to 3, and that is greater than 1. And so since the common ratio is greater than 1, we know that this geometric series is going to diverge. And so that is going to be our final answer. This series diverges. All right, and it diverges because the common ratio is greater than 1. If it was less than 1, then we would know that this series converges, and we would be able to calculate the value that it converges to, also known as the sum of the series. All right, and so that's it for this example. We found the geometric series for these terms, and we concluded that it diverges. As we would add more and more terms for this series, the sum is not going to reach a specific value, it's just going to increase forever. Let's look at another example. All right, so here's our next example. We want to determine the convergence of this series. We have the sum from n equals 0 to infinity of 1/4 to the power of n. All right, so right away, we can see that we have a geometric series because we have a series in the form of some constant multiple, in this case 1, times a value to the power of n. And so when you see a series in this form, you know it's a geometric series, and you can determine if it converges based on the common ratio, which is the value that is raised to the power of n. And so in this case, we can see that r is equal to 1/4. And so let's look at the absolute value of r. That's going to be equal to the absolute value of 1/4, which is just equal to 1/4, and 1/4 is less than 1. And so since that is less than 1, we know that this geometric series will converge. And so we can say that the sum from n equals 0 to infinity of 1/4 to the power of n will be equal to a divided by 1 minus r. Now in this case, a, that constant multiple, is just 1, so we can rewrite that to be 1, and we know that r is equal to 1/4, and so we'll rewrite that with 1/4, and so now we can evaluate this. That will be equal to 1 divided by 3/4, because 1 minus 1/4 is 3/4, and 1 divided by 3/4 is just going to be the reciprocal of this fraction, and so if we flip the numerator and denominator for 3/4, we will have that this is equal to 4/3. And so we can conclude that our geometric series, 1 divided by 4 to the power of n, converges, and it converges to 4/3. All right, so if you want to make a note of that, you can write that it converges to 4/3. Okay? So here's our next example. We want to determine the convergence of this series. We have the sum from n equals 0 to infinity of 1/6 to the power of n plus 1. All right, so now to start, it looks like we have a series that is in the form of a geometric series, although the power of 1/6 is not just n, it's n plus 1. And so that doesn't quite match the form, but we can manipulate this to be in the correct form of a geometric series. Instead of having n plus 1, we can change this to just be n. And we can do that by splitting up this power. And so here's what I mean by that. This would be equal to the sum from n equals 0 to infinity of 1/6 to the power of n times 1/6 to the first power. Right? When you multiply two values that have exponents with the same base, you add the exponents, right? If you have x squared times x cubed, that's equal to x to the 5th power because you added 2 and 3. And so the same would apply for 1/6 to the power of n and 1/6 to the first power. We would add those exponents and have n plus 1. So we can break that up, and now we just have 1/6 times 1/6 to the power of n. And so if I rewrite that a little bit, this would be equal to the sum from n equals 0 to infinity of 1/6 times 1/6 to the power of n. And now we have a series that is in the form of a geometric series. We can see that a, the constant multiple, is equal to 1/6, and r, the common ratio, or the value that is being raised to the power of n, is also 1/6. And so if we look at the absolute value of r, that would be equal to the absolute value of 1/6, which is just equal to 1/6, and that is less than 1. And so we can conclude that this geometric series is going to converge because the absolute value of r is less than 1. And so we know that this is going to be equal to a, which is 1/6, divided by 1 minus r, which is also 1/6. And so if we simplify, this will be equal to 1/6 divided by 5/6, because 1 minus 1/6 is 5/6. And then remember, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so this would be equal to 1/6 times 6/5, which is the reciprocal of 5/6. We just swap the numerator and denominator to get 6/5. And then we can see that these 6's will cancel out, and we'll be left with a final answer of 1/5. And so we can see that this geometric series will converge to 1/5. And so you could write that as your final answer. We could say that this series converges to 1/5. All right, let's look at another example. Okay, so here's our next example. We want to determine the convergence of this series. We have the sum from n equals 1 to infinity of 1/2 to the power of negative n plus 1. All right, so just like with the previous example, this series is close to being in the form of a geometric series, but it's not quite there. And so we need to manipulate what we have just a little bit. In fact, we can split up this power just like we did in the previous example. And so if we do that, this will be equal to the sum from n equals 1 to infinity of 1/2 to the power of negative n times 1/2 to the first power. All right, now if we simplify a little bit, I'm going to bring this 1/2 out to the front. So this will be equal to the sum from n equals 1 to infinity of 1/2 times 1/2 to the power of negative n. All right, now be careful. This is still not in the form of a geometric series. We have the power of negative n. And so let's try to simplify that further and see if we can get rid of that negative. If we take the numerator and denominator to the power of negative n, we will find that this is equal to the sum from n equals 1 to infinity of 1/2 times 1 to the power of negative n divided by 2 to the power of negative n. Now 1 to the power of any finite value is just going to be 1. And so we would say that 1 to the power of negative n would just be 1. And now we have 1 divided by 2 to the power of negative n, and we can make that exponent positive by moving this to the numerator. And so if we continue our work up here, this will be equal to the sum from n equals 1 to infinity of 1/2 times 2 to the positive power of n, right? We move this 2 with a negative exponent to the numerator, and now that exponent is positive. And now we have a series that is in the correct form for a geometric series. In fact, we could rewrite this a little bit better. We could just have 2 to the power of n, and now you can see a little bit better how it resembles the form of a geometric series. And so now we can see that 1/2 is our value of a, so a equals 1/2, and the common ratio r will be equal to 2, right? That value of 2 is being raised to the power of n. And so now, if we look at the absolute value of r, that's equal to the absolute value of 2, which is just equal to 2, and 2 is greater than 1. And so since the common ratio is greater than 1, not less than 1, we know that this geometric series is going to diverge. All right, so in this case, it's not going to converge to a specific value. We will say that the series diverges. Okay, and that is the case even though, and you probably noticed this, our geometric series here doesn't start at n equals 0 like it normally would, right? So far we had only been looking at geometric series that start at n equals 0, but in this case, even though it starts at n equals 1, that doesn't matter. Since the common ratio is greater than 1, the series is still going to diverge. Okay, so the fact that the series didn't start at n equals 0 didn't matter for the case when a geometric series diverges, but it is going to matter when the geometric series is going to converge due to the common ratio being less than 1. And so let's take a look at an example of that. All right, so here's our next example. We once again want to determine the convergence of this series. In this case, we have the sum from n equals 3 to infinity of 3 to the power of n plus 1 divided by 4 to the power of n. All right, so this originally does not look like a series that is in the form of a geometric series. However, we can manipulate it a little bit and see that it will be a geometric series. And so the first thing I see that we can do is split up this power here. We'll have that this is equal to the sum from n equals 3 to infinity of 3 to the power of n times 3 to the power of 1 divided by 4 to the power of n. Okay, so we split up that power and we just have 3 to the power of n times 3 to the power of 1. Now if we pull that 3 to the front, this will be equal to the sum from n equals 3 to infinity of 3 times 3 to the power of n divided by 4 to the power of n. Okay, so this is the same thing we have up here. I just moved this 3 to the first power to the outside of the fraction, and now we can better see what our common ratio will be. We have a fraction where the numerator and the denominator are both raised to a power of n, and so we can just take that whole fraction to the power of n, and we would have that this is equal to the sum from n equals 3 to infinity of 3 times 3/4 to the power of n. All right, and so now you can see that this series is in the form of a geometric series. Specifically, that a is equal to 3, right? That's our constant multiple. And r, the common ratio, is equal to 3/4. And so now if we look at the absolute value of r, the absolute value of r will be equal to the absolute value of 3/4, and that's just equal to 3/4, and that is less than 1, which means that our geometric series is going to converge. All right, and so normally, when we know that our geometric series is going to converge, we would say that it's equal to a divided by 1 minus r. However, that's only the case when your geometric series starts at n equals 0. In this case, our series starts at n equals 3, which is not 0, and so we have to make an adjustment to our calculation. Now, thankfully, it's not a very hard adjustment. All we have to do is calculate the first term of our series and use that as the numerator of this calculation instead of a. All right, so let's erase a. We're not going to use that. Instead, we want the first term of our series. And so since we're starting with n equals 3, that will be the term a sub 3. That is what we want to divide by 1 minus r. And so let's do a little side work. A sub 3 is going to be equal to the value of this expression when n equals 3. So we'll have 3 to the power of 3 plus 1 divided by 4 to the power of 3. And so if we simplify, this is equal to 3 to the power of 4 divided by 4 to the power of 3. And 3 to the power of 4 is equal to 81. So this is equal to 81 divided by 4 cubed, which is 64. And so we have 81 divided by 64. Okay, so that is a sub 3, the first term of our series. And so that's what we're going to use in the numerator of this calculation to find the sum of our series, or what it converges to. And so this will be equal to 81 divided by 64 divided by 1 minus r, which is 3/4. And 1 minus 3/4 is 1/4. So this is equal to 81 divided by 64 divided by 1/4. Now remember, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so this is equal to 81/64 times 4 divided by 1. Now 4 is a factor of 64, so if we divide 4 and 64 by 4, that is equal to 16, and so this reduces to 81/16. All right, and so 81/16 is the sum of this geometric series, or you could see it as the value that the series converges to. So you could also write that the series converges to 81/16. Okay, let's look at another example. All right, next up we want to determine the convergence of this series. We have the sum from n equals 1 to infinity of -1 to the power of n divided by 2 to the power of n. All right, so once again, we have a series that sort of looks like it might be in the form of a geometric series, but not quite. We're going to have to change how it looks just a little bit. In this case, notice that both the numerator and denominator are raised to a power of n, and so we could rewrite this series to be the sum from n equals 1 to infinity of -1 divided by 2 to the power of n. Okay, so since both the numerator and denominator were raised to that power, we can just take that whole fraction to the power of n. And so now you can see that we have a series in the form of a geometric series. We can see that a will be equal to 1. That's the constant multiple for this series. We just have 1 times this value to the power of n. And that value that is being raised to n is the common ratio r. R is equal to negative 1/2. And so now if we look at the absolute value of r, that will be equal to the absolute value of negative 1/2, which will make that positive 1/2. And positive 1/2 is less than 1, which means that our geometric series will converge. However, note that like the previous example, this geometric series does not start at n equals 0. It starts at n equals 1. So this is not going to be equal to a divided by 1 minus r. We need to replace a with the first term of our series. And so since our series starts at n equals 1, that's going to be the term a sub 1. All right, and so let's calculate a sub 1 for our series. A sub 1 is going to be equal to negative 1/2 to the first power, which is just equal to negative 1/2. All right, so that's the term of our series when n equals 1. And so that's what we will use as the numerator of our calculation for the sum of the series, since we know it converges. And so this will be equal to negative 1/2 divided by 1 minus the common ratio, which is negative 1/2. Now if we simplify, 1 minus negative 1/2 will become 1 plus 1/2 because those negatives will cancel out. And so this is equal to negative 1/2 divided by 1 plus 1/2. And 1 plus 1/2 is 3/2. So this is equal to negative 1/2 divided by 3/2. And dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So this is equal to negative 1/2 times 2/3. That is the reciprocal of 3/2 if you flip the numerator and denominator. And then these 2's will cancel out and leave us with an answer of negative 1/3. And so we can say that our geometric series converges to negative 1/3. That will be our final answer. The series converges to negative 1/3. All right, and so we have determined the convergence of the given geometric series. All right, here's our next example. We want to determine the convergence of this series, and we have the sum from n equals 0 to infinity of 3 to the power of n plus 7 to the power of n divided by 9 to the power of n. All right, now in this case, it looks like we might have a geometric series, but we do need to manipulate our expression a little bit. We can actually split up this fraction into 2 fractions because we have 2 terms added together in the numerator divided by the same denominator. And so here's what this looks like if we split it up. We'll have that this is equal to the sum from n equals 0 to infinity of 3 to the power of n divided by 9 to the power of n plus 7 to the power of n divided by 9 to the power of n. Right, so we just split up the fraction into 2 fractions by taking the first term in the numerator and dividing it by the denominator to get this part. And then we take the second term of the numerator and divide it by the denominator to get this term. Okay, so we have 3 to the power of n divided by 9 to the power of n plus 7 to the power of n divided by 9 to the power of n. And so now what we can do is, since we are taking the sum of both of these terms individually, we can actually split this up into 2 separate sums or 2 separate series. We can have the series for this term plus the series for this term. So this will be equal to the sum from n equals 0 to infinity of 3 to the power of n divided by 9 to the power of n plus the sum from n equals 0 to infinity of 7 to the power of n divided by 9 to the power of n. All right, so now we have 2 different series to work with. And it looks like both of them are geometric series. All we have to do is rewrite them just a little bit. Both the numerator and denominator in both series are raised to the power of n, and so we can just take that whole fraction to the power of n. So we'll have that this is equal to the sum from n equals 0 to infinity of 3/9 to the power of n plus the sum from n equals 0 to infinity of 7/9 to the power of n. Now 3/9 will reduce to 1/3, and so I'm just going to rewrite that to be 1/3. So we have 1/3 to the power of n, and now we have 2 geometric series that we can determine the convergence of. For both series, the value of a, or that constant multiple, is equal to 1. but the common ratios in each series is going to be different. For the first series, the common ratio r is equal to 1/3, and for the second series, the common ratio is equal to 7/9, right? Those are the values that are being raised to the power of n. And so now in both cases, if we were to look at the absolute value of r, you can see that since both of them are positive, the absolute value is just going to be those values, and both of them are less than 1, right? 1/3 is less than 1, and 7/9 is less than 1 as well. And so because of that, both of the series are going to converge. We can calculate the sum of each series by using that formula of a divided by 1 minus r. And so remember, in both cases, that a is equal to 1, and so we will have that this is equal to 1 divided by 1 minus 1/3 plus 1 divided by 1 minus 7/9, right? We just have a, which is 1, divided by 1 minus the common ratio for each geometric series. And so if we simplify, this is equal to 1 divided by 2/3 plus 1 divided by 2/9, because 1 minus 1/3 is 2/3, and 1 minus 7/9 is 2/9. And remember that 1 divided by a fraction is just going to be the reciprocal of that fraction. So we'll have that this is equal to 3/2 plus 9/2, right? The reciprocal of 2/3 is 3/2 if we flip the numerator and denominator, and then the reciprocal of 2/9 is 9/2. Now 3/2 plus 9/2 is going to be equal to 12/2, which is equal to 6. And so 6 is the sum of this series. In fact, it's the combined sum of two separate geometric series. All right, so in the end, we can conclude that our original series converges to 6. Okay, so that is the final solution for this example. Let's look at a different example. All right, so now we're going to look at an example of an application of a geometric series. What we can do with a geometric series is rewrite a repeating decimal as a fraction. And so for this example, we want to use a geometric series to express 0.7 repeating as a fraction. And so here's how we're going to do that. 0.7 repeating is equal to 0.7777777 and so on. And we can rewrite that with an infinite sum of fractions. And so here's what that looks like. We will have 7/10 plus 7/100 plus 7/1000, and we can continue on from there. And so the reason why these two expressions are equal is because 7/10 is 0.7, 7/100 is 0.07, and 7/1000 is 0.007. And of course, we're adding those together, and that would continue on forever. And so you can see, if we were to add the decimal values of these fractions together, that we would slowly create this repeating decimal. And so as we continue to add more and more of these fractions, where that denominator increases by a factor of 10, we can form this repeating decimal. And so what we can do is rewrite this infinite sum of these fractions as a geometric series. And so here's how we're going to do that. The first step is to pull out the first term out of every term of the series. If you set it up correctly, that first term will be a factor of all of the other terms. And so if we pull out 7/10 from the rest of the terms, the first term will become 1, then that will be added to 7 divided by 100 divided by 7/10, and that will be 1 divided by 10, right? 7 times 1 is 7, 10 times 10 is 100. So 7/100 divided by 7/10 will be 1/10, and then that will be added to 1/100, and so on. All right, 7 times 1 is 7, and 10 times 100 is 1,000, and so 7/1000 divided by 7/10 is 1 divided by 100. All right, now if you look closely at these terms, we now have a geometric series that we can work with. And you can see it more easily if I were to rewrite some of the terms. We could rewrite 1 to be 1 divided by 10 to the power of 0, because 10 to the power of 0 is 1, and so 1 divided by 1 is 1. Then we could add that to 1/10, or 1 divided by 10 to the first power, and then add that to 1 divided by 10 squared, because 10 squared is 100. and that would continue on from there. Each subsequent fraction would be 1 divided by 10 to a power 1 more than the previous term, right? We have 10 to the power of 0, 10 to the first power, 10 squared, and then we would have 1 divided by 10 cubed, and so on. And so this is a geometric series that we can represent pretty easily. This will be equal to 7/10 times the sum from n equals 0 to infinity of 1 divided by 10 to the power of n. Right? The only value that's changing for each of these terms is the power of 10, and so we have 1 divided by 10 to the power of n, where n starts at 0. Okay, so now if I clean up my work here, we can rewrite 1 divided by 10 to the power of n to just be 1/10 to the power of n, right? If we have 1/10 to the power of n, that would be equal to 1 to the power of n divided by 10 to the power of n, and 1 to the power of n, where n is a finite number, is just going to be equal to 1. So this is equal to 1 divided by 10 to the power of n, which is what we have right here. And so we can rewrite that to be 1/10 to the power of n. And so if we do that, this will be equal to 7/10 times the sum from n equals 0 to infinity of 1/10 to the power of n. And so now we have a geometric series that we can determine the convergence of. And so note that the common ratio, or the value being raised to a power of n, is 1/10, right? R is equal to 1/10. The absolute value of R would still be 1/10, and 1/10 is less than 1, and so we know that this geometric series will converge. And so we can calculate the sum of that series by using the formula of a divided by 1 minus r. Now in this case, a is just equal to 1, or I guess you could say it's equal to 7/10, but it doesn't really matter. Either way, you're going to get the same solution. And so this will be equal to 7/10 times 1 divided by 1 minus r, which is 1/10. Okay? If you were to multiply 7/10 back into this series, then 7/10 would be your constant multiple, or the value of a in the numerator. It doesn't matter. This calculation will still get the correct answer. And so if we simplify, this will be equal to 7/10 times 1 divided by 9/10, because 1 minus 1/10 is 9/10, and 1 divided by a fraction is just going to give us the reciprocal of that fraction. And so this is equal to 7/10 times 10/9, and those 10s will cancel out and give us a final answer of 7/9. And so 7/9 is the fraction that represents this repeating decimal of 0.7 repeating. And you could check that out in your calculator if you'd like. If you divide 7 by 9, you will find that it's equal to 0.7 repeating. Okay, so that's how you express a repeating decimal as a fraction by using a geometric series. Let's look at one more example for this video. All right, here's our last example. We once again want to use a geometric series to express a repeating decimal as a fraction. In this case, we have 0.14 repeating. So this is a little bit different. Instead of just having one decimal value that's repeating, we have two. And so 0.14 repeating is equal to 0.14, 14, 14, 14, and so on. All right, and so representing this decimal as an infinite sum of fractions is going to be a little bit different than it was when we just had 7 repeating. And so here's how we're going to do this. We're going to break it up based on where 1 and 4 are together. And so what I mean by that is we are going to make a fraction for each grouping of 1 and 4. Now I'm only going to do the first 3, but you could continue on forever. This first part, 0.14, that is going to be 14 divided by 100, right? That's because 0.14 takes us to the hundredths place. Now if we look at the next 2 decimal places, we are at the thousandths place and then the 10,000ths place, and so our next fraction will be plus 14 divided by 10,000. Now for our third one, we go from the 10,000ths place to the 100,000ths place to the millionths place. So our next fraction will be plus 14 divided by 1 million. All right, so that is going to be the last fraction that we write down, but this would continue on forever. Okay, and so just as a reminder, 14 100ths is 0.14, 14 divided by 10,000 is 0.0014, and 14 divided by 1 million is 0.000014. And so if we add those decimals together and then more after that, we will slowly build this repeating decimal. Okay, and so now what we want to do is rewrite this infinite sum of fractions with a geometric series. And so the first thing I'm going to do is rewrite all of these denominators to be powers of 10. That's always going to be your go-to when you are using a geometric series to rewrite a repeating decimal as a fraction. And so 100 is 10 squared, so we have 14 divided by 10 squared. 10,000 is 10 to the fourth power, so we have 14 divided by 10 to the fourth power. And then 1 million is 10 to the sixth power, so we have 14 divided by 10 to the sixth power. And that would continue on from there. And so you can see that each power of 10 is increasing by 2 with every fraction. So just keep that in mind. That's going to come into play later. But now what we want to do is pull out a common factor of the first term from every term in the series. And so if we do that, this will be equal to 14 divided by 10 squared times 1, because 14 divided by 10 squared divided by itself is 1. And then for our next term, 14 divided by 10 to the fourth power, if we pull out 14 divided by 10 squared out of that, we will be left with 1 divided by 10 squared, right? That 14 is taken out, and 2 of the 10s are taken out from the denominator, and so 4 minus 2 is 2, so we're left with 10 squared. And then our next term, we will have 1 divided by 10 to the fourth power if we divide out 14 divided by 10 squared, because that 14 is taken out, and we take out 2 of those 10s, and so 6 minus 2 is 4, so we have 10 to the fourth power, and we would continue to add on from there. All right, now if I clean up my work, we can now work on rewriting this series of terms as a geometric series. All right, and so remember that we can rewrite 1 to be 1 divided by 10 to the power of 0, because 10 to the power of 0 is 1, and 1 divided by 1 is still 1. And so if this first term is when n equals 0 for our geometric series, the second term is when n equals 1, and the third term is when n equals 2, notice the relationship between the value of n and the power of 10. For the first term, we just have 0 and 0, but from there on out, we have 1, and then 2, and then 2, and then 4. So it looks like the pattern is that we multiply the value of n by 2 to get the power of 10, right? 2 times 0 is 0, 2 times 1 is 2, and 2 times 2 is 4. And so our geometric series will look like this. We'll first have that 14 divided by 10 squared, or at this point we can just rewrite that to be 100, so we'll have 100, times the sum from n equals 0 to infinity of 1 divided by 10 to the power of 2n. Okay, so remember we're multiplying the value of n by 2 to get the powers of 10, and so 2n will be that power. All right, and so now we have our geometric series, but we can rewrite this a little bit. Let me show you what I mean. This will be equal to 14 divided by 100 times the sum from n equals 0 to infinity of 1 to the power of 2n divided by 10 to the power of 2n. Right, this goes back to what we've been doing in previous examples. Remember that I said that 1 divided by 10 to the power of n is equal to 1 to the power of n divided by 10 to the power of n, which is just equal to 1 divided by 10 to the power of n, because 1 to the power of n is just going to be 1 as long as n is finite. And so you can take 1 divided by 10 to the power of n and rewrite it in either of these forms. Now in this case we have 2 times n as our power, but we don't want to have that for our actual geometric series. What we can do is actually use one of the properties of exponents. Remember that if we have an exponent like x and it's being squared and then that is being cubed, we would multiply those exponents. And so you'd have 2 times 3, which would give us x to the 6th power. And so we can kind of reverse that process and rewrite 1 to the power of 2n to be 1 squared to the power of n, right? You would multiply those exponents and you would still have 2n. And so we can do the same in the denominator. We will have 10 squared to the power of n. The exponent would still be 2n because we multiply those exponents. But now we can see the power of n that can be applied to this whole fraction. So now if I clean up my work again, this will be equal to 14 100ths times the sum from n equals 0 to infinity of 1 squared divided by 10 squared to the power of n. All right. And now 1 squared is just equal to 1, and 10 squared is equal to 100, And so we'll just rewrite this to be 1/100th, and then we will have successfully rewritten those terms into a geometric series. And so now all that's left to do is to make sure that this series converges and then calculate its sum to finalize the fraction that will represent this repeating decimal. All right, so in this case, for this geometric series, we can see that the value being raised to the power of n is 1 divided by 100. So that's our common ratio. So r is equal to 1 divided by 100. The absolute value of that value is still 1 divided by 100, and 1 divided by 100 is less than 1. And so we know that this geometric series will converge, and so we can calculate its sum using that formula. So this will be equal to 14 divided by 100 times a, which is just 1. 1 is the constant multiple being multiplied by our common ratio to the power of n. So we have 1 divided by 1 minus the common ratio of 1 divided by 100. And now if we simplify, this is equal to 14 divided by 100 times 1 divided by 99 100ths, because 1 minus 1 100th is 99 100ths. And 1 divided by a fraction will be equal to the reciprocal of that fraction. And so we'll rewrite this to be 100 divided by 99. And now we can see that these 100s will cancel out, and our final answer is equal to 14 99ths. And so 14 divided by 99 is the fraction that represents this repeating decimal. If you plug 14 divided by 99 into your calculator, you will get 0.141414 and so on. All right, and so that's how we use a geometric series to rewrite this repeating decimal as a fraction. Okay, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.